I wanted to talk a bit about, in a sense, it's a story about how philosophy ended up being important in technology development and in making something that somehow is related to artificial intelligence. So it's kind of a funny story which I'm only starting to understand. I should say that I was sort of introduced to philosophy early in life because my mother was a philosophy don in Oxford, and I always used to say that if there was one area of human endeavor that I would never get involved with, it was philosophy. And so it was sort of, in a sense, embarrassing, I don't know, a decade or more ago, when I started seeing philosophy papers that were based on science that I had done. So these things evolve. Well, what I wanted to tell you about was a little bit about how Wolfram Alpha sort of emerged from, in a sense, what could be thought of as sort of philosophical considerations about computing. So let me just introduce a little bit to Wolfram Alpha. The idea of Wolfram Alpha is something very ambitious. It's to try and make as much of the world's knowledge as possible computable. So what I mean by that is that there's lots of things, there's lots of knowledge that's sort of been accumulated in our civilization, but much of that knowledge is kind of locked up in the minds of human experts. And the only way in which a typical person can access that knowledge is to go ask the question to a human expert. One of the things that's happened in the progress of technology is we've been able to automate more and more things. But one of the things we haven't yet automated is this process of sort of extracting knowledge from experts. So actually, this was a project that I had first started thinking about probably 30 years ago, sort of to what extent could we really take all that knowledge, all that sort of systematic data, all those methods and algorithms and so on that have been accumulated in our civilization and make all that stuff sort of computable and automatically accessible. But at the time, I had kind of assumed that the only way to make a system that could do this was to sort of solve the general artificial intelligence problem, that the only way to deal with all of that sort of knowledge was to build something that sort of thinks like a human and does kind of an artificial version of the kind of intelligence that we humans have. Well, that was what I thought 30 years ago. Through a kind of circuitous route that perhaps I'll describe that went through a lot of basic science development that I did, I finally realized a few years ago that perhaps that wasn't quite right, and perhaps there was practical technology and sort of a framework for constructing something that could really make a lot of the world's knowledge computable without immediately solving the problem, without sort of doing the thing that got done with flight of making planes that fly without solving the problem of knowing how birds manage to fly. Well, let me show you a little bit about what Wolfram Alpha does. Kind of the idea is we can start off with sort of formal kinds of knowledge, like things about mathematics and so on, where we kind of know that it's possible to compute answers, and Wolfram Alpha is based on Mathematica. Mathematica is the system that we've developed over the last 25 years, whose main objective is to sort of make formal computation, to provide a systematic language for doing formal computation. And Mathematica gets used these days by a large fraction of the world's sort of high-end R&D folk across lots of kinds of fields and industries and so on. Mathematica concentrates on making a very precise language for doing sort of formal computation. One of the things that we've been interested in Wolfram Alpha is to kind of take all that messy knowledge that exists in the world and try and make that computable, which is sort of a somewhat different goal than the goal in Mathematica. But one of the things that we can do in Wolfram Alpha is take sort of do mathematical computations and things where we could perhaps say, you know, what's the integral of this, and we'll compute the answer, and then we can work out, Wolfram Alpha will sort of volunteer some information that it thinks might be interesting if you had just done that integral. So what I was showing here was just computing an integral, for example. You know, you could ask Wolfram Alpha, I don't know, you type in some number here, and it'll probably be able to tell you things like it'll be able to say, well, here are some possible closed forms that number, possible mathematical expressions that could correspond to that number. But we can go and start asking it things not just about sort of the formal world, but about the actual world, so to speak. We could say, you know, what's the GDP of France? And it'll show us the result. Or we could say something like, what is the GDP of France divided by UK, for example? And we as humans can pretty much understand what that means, and so can Wolfram Alpha, and it gives us the result and shows us a plot and so on. Or we could say, I don't know, let's see, what city are you guys in York. Let's ask it about York. It'll know a certain amount about York. It'll guess that we're talking about York as a city rather than a surname or a given name. I haven't heard of, let's see, York as a given name. Let's see what that tells us. Okay, so York is a rare, look at that. It was a given name that might have been slightly common in the late 1800s, but seemed to have fallen out of favor since then. But let's go back to York as a city. So now we know a certain amount about York as a city, and we could, there's a map. Oh, it seems like it's fine weather there, 70 degrees Fahrenheit and so on. We know that where York is roughly relative to other cities. Okay, there's a list of some notable people born in York and so on. Quite a distinguished looking list there. Or we could say something like, York weather. So now that's a plot of the temperature as a function of time for the past week. Or maybe we could go ahead and ask it, what's been the temperature for the past 10 years in York? Or we could go and ask it, I don't know, York, UK to Concord, Massachusetts. It'll tell us that it's 3,200 miles between where you are and where I am, and so on. Or we could like type in, I don't know, some sequence like this, and it'll guess that we're probably talking about a base pair sequence on the human genome, and it'll tell us, should be able to work out where on the human genome that particular base pair occurs, and so on. So Wolfram Alpha by now knows about lots of different kinds of things in the world, things, scientific things, socioeconomic things, all sorts of stuff. We can ask it all kinds of questions that we might in the past have sort of assumed required kind of thinking to figure out, but we, in a sense, we take a point of view that in a sense, one could think about answering some of these questions by kind of a reasoning approach. What we tend to do is to say, what are the sort of best methods that have been developed in the course of science and engineering and so on? Let's try and make use of all those methods to get to the answer. So, but you can still ask, I don't know, let's say P and not Q or R or something like that. Let's see what that does. Okay, so there's a truth table, and there are some alternative forms for that logical expression and so on, and we can compute all kinds of things like this. Okay, so this is a big project, and I can talk about sort of what's involved in trying to make the world's knowledge computable in this way. There are many components about sort of being able to ingest data about lots of kinds of things, curating that data, organizing it, validating it, making it computable. There are issues about sort of implementing all the methods and models that exist that have been developed in lots of different areas. There are issues about understanding the natural language that people choose to type into that little input field. That's been sort of an area where we've been able to make some fairly major progress in actually understanding kind of the strange pidgin language that people choose to ask their questions in. I think it's often quite a direct reflection of the way people think about things. They'll type something in, and then they'll kind of have an afterthought about something else, and they'll type that in too. And we have to kind of decode what the human thinking was behind that. And then there's the question of, well, we can compute all this stuff. What should we choose to show as the answer? And that's a whole other set of algorithms and methods and heuristics and so on involved in doing that. Well, okay, but I said I would try and explain sort of something about kind of the how I got to decide that this project was not absolutely impossible, because it had seemed for years to me that such a project would be just absolutely impossible. So that story kind of starts with a bunch of work that I did in basic science, and really what happened there was I was interested in areas of natural science where it was a question of explaining phenomena in nature. And I had worked in physics a lot, and in physics, mathematics is sort of the big methodology that gets used to make models of things. And obviously, mathematics over the past 300 years has been pretty successful in letting us make models of lots of kinds of systems in the world. But what I also realized was that there are lots of cases, even in areas like physics, where mathematical methods don't really let us get to the end in making a successful model, particularly when the systems appear to have very complex behavior of one kind or another. So I got interested in the question now, more than 25 years ago, of sort of, if 30 years ago actually, the question of what, if one was going to make models of systems, for example, in nature, what kind of raw material should one make those models out of? And so what I thought about was what sort of the most general possible space of models that one could consider for systems in nature or elsewhere. Is it just mathematics, or is there more to it? Well, what I realized is that actually if one's going to have a theory about a system, that it had better be the case that there are some underlying rules that govern the operation of the system. But the question is sort of what's the most general space of those rules? Well, conveniently in modern times, we have sort of a paradigm, a framework for thinking about the set of possible rules, and it's computer programs. We think, and we can discuss in more detail in what sense this is the case, that sort of any possible definite rule can be represented in some way by some kind of program. So the question is, if we think that there might be programs that govern how systems, for example, in nature work, what might those programs be like? Well, the programs that we're used to as a practical matter of using computers, they're long, complicated programs that we build for very particular tasks. We write a giant program, you know. By now, Wolfram Alpha, for example, is 20 million lines of Mathematica code long. It's a very big, sort of very special program. But the question that we might ask in terms of natural science is, what does the space of all possible programs look like? For example, it's sort of a basic science, natural science kind of question. What's out there in the computational universe of possible programs? And that's something that, so then we have to start sort of saying, well, what might these very simple programs out there in this computational universe of possible programs look like? Well, a particular class of programs that I started off studying a long time ago and still find the most convenient for explaining what's going on are these things called cellular automata. And a typical cellular automaton is a very simple thing. It's just got a line of black or white cells, and the system evolves in a sequence of steps down the page here, just at each step using a particular fixed rule to determine what the color of a cell should be on the next step based on the color of the cell on the step above it, on the step above it and the cells to its left and right. So you can see at the bottom of the screen here a rule that says, for example, the case on the left says if there are 3 black cells above, then put down a black cell below. And then you start off from a single black cell at the top of the screen and then let that rule be applied down the page. And the result you get is that this very simple rule, starting off from just that very simple single black cell, produces a very simple pattern. Nothing surprising. This is kind of sort of exactly what one might have expected from sort of an intuition about how things work. Let's say you change that rule just a little bit. This is what you get in that case. Again, I just changed one case in the rule, and starting now from a single black cell, I wind up getting this kind of checkerboard pattern. Again, you might say, simple rule, simple initial condition, simple result, everything's working as expected. Well, then you keep going a little while longer. Let's say you change another couple of cases in the underlying rule. This is what you get. You start off from just one black cell at the top, and you don't get such a simple uniform pattern. You get some kind of nested pattern. Keep going a little while longer, you get something like this. It's a nested fractal pattern. And again, you might have the theory, okay, simple rule, simple initial condition, everything must ultimately be simple in the sense that, for example, we as humans can ultimately perceive that there's a very regular pattern. We could sort of summarize this pattern in a very straightforward way. And one could say, so the simplicity in, simplicity out. Well, okay, so a long time ago I decided, let me sort of turn the sort of computational telescopes that I've developed as practical tools like Mathematica, let me sort of turn these computational telescopes out into this computational universe and just sort of find out in general what's out there. So there's a very simple experiment one can do. One can just take all the possible rules of the kind that are shown at the bottom of the page here, and one can just try every one of those rules and see what kind of behavior is produced. So this is the result. There are 256 of those particular kind of rules. This is the first 64 of them, typical of all of them. This is what one gets. This kind of a minimal computer experiment about what's out there in the computational universe. Well, so what we see is there's quite diverse different things that happen. Most of what happens is pretty trivial. Mostly it's kind of sort of what we would expect. Simple rules, simple initial conditions, simple behavior. But if you look at this experiment, you'll notice that, for example, the 30th one of these rules looks a bit more complicated. And if we look at that in more detail, here's the rule 30 cellular automaton. We start off from just one black cell. We let it evolve down the page according to that rule that's at the bottom of the screen there, and we get this somewhat more complicated pattern. Well, we might say it's a simple rule. There must be some way of seeing the simplicity of that underlying rule in the behavior that's produced in the system. So let's try running it a bit longer. That's what it looks like. Well, when I first saw this, I tried all sorts of mathematical methods, statistical methods, cryptanalytic methods, all sorts of things like this. Tried to be sort of as clever as possible about analyzing this to try and see whether I could kind of crush this, this sort of output and understand that it came from something very simple. Well, you can see there's some regularity on the left. You can prove all kinds of theorems about that. But the bottom line about this pattern is that many aspects of it look, for all practical purposes, random. So if you look at, for example, the center column of cells down this pattern, it's random, a bit like the digits of pi seem random or something like that. And for example, it's random enough that we've used it as a practical pseudo-random number generator for Mathematica for the last 25 years, and it does really well for that. This is, to me, a very remarkable thing. It's something which violated my intuition completely. In fact, it took me several years to kind of come to terms with the fact that this really was something where we were creating complexity from a very simple rule. And so the reason that it sort of feels so wrong is that when we do engineering, for example, we're used to the fact that if we want to make something complicated, we have to go lots of effort, we have to put in complicated plans, we have to build a complicated thing. It's not sort of an effortless process to make all this complicated stuff. Well, it's interesting that even though it's hard for us with our current engineering, it seems to be pretty easy for nature. There are lots of cases in nature where one sees very complicated phenomena, and often we've been led through our sort of experience with engineering and so on to say, if there's a complicated phenomenon, there must have been some complicated process. Maybe it's some elaborate, course of natural selection and evolution. Maybe it's some other complicated process which has led to sort of the complicated output that we see. But what we're seeing here is that that's just not the case. Out in the sort of computational universe of possible systems, it's actually extremely easy to get this kind of complexity. And in a sense, I think this is sort of the secret of nature. I mean, it's been sort of an embarrassing thing for our technology and civilization, so to speak, that if you're shown two objects, one of them is a natural system, one of them is an artifact, and you're asked to guess which is the artifact, which is the natural system, it's a really good heuristic that the one that looks simpler to us is likely to be the artifact, the one that looks more complicated is likely to be the natural system. And I think that this is kind of showing us the secret that nature seems to use to make all this complexity in an awful lot of cases. And I've looked at many specific cases we can talk about if people are interested. So in a sense, what's going on is that in doing engineering, we have always tended to concentrate on systems where we can foresee the behavior of the system when we set it up. But if you just look at the sort of computational universe of possible systems, there are lots of systems where it's very difficult to foresee the behavior when you set them up. And if you sort of sample systems at random, then many of the systems will be of that kind. They're not things that we would reach by sort of an incremental process of either engineering or even natural selection in many cases, but they're things that are sort of out there in this computational universe of possible systems. So it's a very general phenomenon that we're seeing here. These are cellular automata. This is a Turing machine, a very simple Turing machine. You don't have to go far in the space of Turing machines before you start seeing all kinds of complicated behavior in the same kind of way as cellular automata. There's nothing very special about cellular automata. You can even sort of go right into the heart of traditional mathematics, look at things like differential equations. Once you know to look for this phenomenon, it's pretty easy to find it all over the place. You can find it even in areas of number theory and so on that have been around for thousands of years. I mean, it's related to things like the randomness of the distribution of primes, which is something that sort of has been certainly known in mathematics, but something where the concentration of mathematics has not been on understanding sort of the randomness of that, but it's been trying to make use of regularities that exist there. And in general, if we look at sort of the progress of lots of kinds of science, physics, for example, what we see is that there are lots of kinds of phenomena which have this feature that they produce sort of complex behavior in the kinds of ways that I'm showing, but they've tended to be avoided by physics, because physics has tended, like many sciences, like many kinds of areas of inquiry, has tended to concentrate on things for which its methods are successful. And its methods have tended to be mathematical methods, and so the areas where physics has been most developed are areas where these traditional mathematical methods work. So what does it mean that when we look at systems like Rule 30, what kinds of phenomena can we deduce from this fact that out in the computational universe it's so easy to make this very complicated stuff? Well, I think there's a general principle I certainly came to from just looking empirically at a lot of what's out there in the computational universe. It's a thing I call the principle of computational equivalence, and here's how it works. So the first thing to realize is that all of these different systems, whether they're simple cellular automata, whether they're systems in nature being modeled by these things, etc., all of these systems can be thought of as performing computations. In effect, for a cellular automaton, for example, there's some input at the top, you then run certain rules for the computation, and then you get the output at the bottom. Well, the question that we get to ask is, if we look at all these different kinds of systems, how do the computations that these different, all of these systems can be thought of as doing computations. How do the computations done by these different systems compare? So the point of the principle of computational equivalence is this, that if we look at all these different kinds of systems, there are some whose behavior is sort of obviously simple, and where the computations that their behavior corresponds to are similarly very simple. But what the principle of computational equivalence says is that above some threshold, all systems are equivalent in terms of the computations that they do. So one of the things, the point then is that as you start sort of tuning up, as you start kind of turning up the complexity of, for example, the underlying rules for a system, you might have thought that as you increase sort of the complexity of what's inside the system, of how the system works, that there will be a gradual increase in the complexity of behavior, the sort of complexity of the computation that the system does. What the principle of computational equivalence says is that no, that's not the case, that above some low threshold, you immediately jump to the situation where all systems are equivalent in the sophistication of the computations that they do. Okay, so this is a general principle. It has a sort of complicated epistemological character, which we can talk about. It's a little bit like something like the Second Law of Thermodynamics. It's sort of a mixture of a provable mathematics-style law, kind of a definitional kind of thing, kind of something that's like a law of nature. It's a little bit complicated epistemologically, but we can talk about that. But it has many, we have this principle, it has many kinds of predictions. So one prediction is that it suggests that above this very low threshold in sort of the complexity of the underlying rules, we'll commonly find systems that are capable of universal computation. So in the case of these simple cellular automata, we know that this is a particular cellular automaton. This is the rule 110, the 110th cellular automaton rule that works in the same way as rule 30. Here it's starting off from random initial conditions. Well, with great effort, it's possible to prove that this particular system is capable of universal computation. You can kind of see that this is plausible because you can see that there are these little structures running around that seem like they might be doing logic operations and so on. And yes, you can show in the end that you can construct a tag system, and from the tag system you can construct a Turing machine and so on from this. So already we know that out at the 110th rule in this computational universe, there's universal computation. That's something we would expect from this principle of computational equivalence. You don't have to go very far before you get sort of systems of equivalent sophistication to anything else. Well, you could ask, for instance, about Turing machines there. In fact, I was interested in what's the simplest possible universal Turing machine. This, if you just sort of sample the space of possible Turing machines, the very simplest set of 4096 two-color, two-state Turing machines, you can prove none of those can be universal. Already, by the time you've got 3 colors and 2 states, there's a nice candidate for a universal Turing machine. I'd wondered for a number of years whether, in fact, this was universal. So we put on a little competition a few years ago, and actually in a rather short time, a young person who I guess is based in Manchester, is that right? Managed to successfully prove that yes, indeed, this Turing machine is the sort of simplest candidate for being universal Turing machine is actually universal. So this is sort of the threshold of universality in Turing machines. And just like in cellular automata, and just like we would expect from this principle of computational equivalence, the threshold of universality is very low. in the space of all possible systems. So that's kind of good evidence for this principle of computational equivalence. Well, let's assume the principle is true. What other implications does it have? Well, one of its implications is a phenomenon I call computational irreducibility. And so when we look at a system like this, well, when we think about traditional science and traditional physics and so on, one of the great triumphs of traditional physics is this idea that we can predict things. When you look at celestial mechanics and you look at some idealized planet going around an idealized star, you could say, an idealized Earth, you want to know where it is a million years from now, you don't have to trace a million orbits of the planet. You can just essentially fill into some formula the number a million, and you immediately know where the planet is going to be. So there's sort of a shortcut way, a way to reduce the computational effort that the system itself goes through to work out its behavior. It's computationally reducible, so we can make a sort of a quick shortcut prediction. We can use kind of our computational sophistication to outrun the computations that are being done by the system itself and sort of get to the outcome more efficiently than for the system. But when we look at something like Rule 30, it's much less clear that we can do that. And in fact, what we realize is that that isn't the case. One of the things the principle of computational equivalence implies is that many of these systems will be irreducible, in the sense that to work out how they behave after a certain number of steps, the only real way we can do that is effectively to do a computation that's equivalent to the one the system itself does, to follow through all those steps and see what happens. So this is something that has, I think, lots of implications. It has lots of practical implications for science. Simulation is a convenient methodology in many areas, but computational irreducibility means it's not just convenient, it's actually necessary. There's no way to know what these systems will do other than by effectively simulating them and seeing what happens. Now, as a practical matter, that puts a lot of pressure on the kinds of models that you use for systems, because if you know you're going to have to follow all the steps, each of those steps better be as efficient as possible. You better have models that do the best possible job in capturing just those features of the system that you care about and not others, and not sort of wasting computational effort sort of in this process. So there are lots of other implications of computational irreducibility. One of them that I find kind of interesting, I should say that sort of computational irreducibility is in some respects sort of a finite time version of things like undecidability. When you have a system that shows computational irreducibility, and there are many details of these definitions that one has to kind of tie up to make all this stuff really work. But at a general level, what one can say is that if there's a system whose behavior is sort of computationally irreducible on a step-by-step basis, then if you ask a question about what will the ultimate behavior of the system be, then that question to ask about sort of the infinite time behavior can be something which cannot be answered in finite time necessarily, and so has to be considered undecidable. Well, another thing one can ask about is and I was looking for a better example here and not finding it. Let me see if I can find one. Let's take something like this. You can ask a question about sort of what will the system choose to do? And as soon as we start saying what will the system choose to do, we're kind of attributing to the system something which is almost a matter of kind of free will about what the system will do. And actually, as we start looking at these systems and thinking about computational irreducibility, we start thinking about things like free will, and we start asking questions like, what does it mean? What is the idea of free will? Well, one of the points is, if we believe that there is a deterministic underlying rule, to say that there's free will is to say somehow that the behavior of the system appears to be free of the determinism that exists in its underlying rules. Well, one of the things that we see with computational irreducibility is sort of an explanation of what can be going on there. While it is the case that the system may be ultimately based on deterministic underlying rules, it may not be possible to predict what the system will do by any procedure that is much more efficient than just following the steps in the behavior of the system and seeing what happens. So it's a case where effectively the system, it's sort of an intrinsic feature of the system what it will do. It's something where we don't have, even though there are deterministic underlying rules, the behavior of the system appears free of those underlying deterministic rules, because the only way to work out what it will do is by effectively just tracing each step and seeing what happens. See, it's one thing about computational irreducibility. What's the ultimate origin of it? Well, in a sense, when we look at a system, if it's going to be computationally reducible, what it means is that we, as observers of that system, must be capable of sort of out-computing the system itself. It must be the case that sort of we're up here as very sophisticated computational entities, and the system is down here as something less sophisticated, and that's why we can kind of outrun the system. That's why the system will look simple to us in its behavior, because we're somehow much more sophisticated than the system itself. And it's that the fact that that often is not the case, which is what's implied by the principle of computational equivalence, which is what makes it be the case that it's irreducibly, that there's a sort of computational irreducibility in working out what the system does. So it's the failure of our sort of differentiation from the system itself that leads to this computational irreducibility. It's sort of an interesting thing in natural science that if we look at the progress of natural science at a fundamental level, a lot of what's tended to happen, whether it's in relativity theory, quantum theory, whatever, has been a consequence of getting more realistic about how observers work. And this is another sort of step in that same process. We've kind of, in effect, implicitly assumed that we as observers are sort of computationally arbitrarily sophisticated relative to the systems that we're observing. But we now realize that that isn't the case, that we're actually just equivalent in many respects to the systems that we're observing. So that has many consequences if you're interested, for example, in thermodynamics. It actually gives us finally an explanation for the second law of thermodynamics as kind of this process where a system will start from a very simple initial state. This is a reversible cellular automaton which kind of emulates the reversibility of microscopic physics. And we'll start from a simple state and we'll end up producing something that appears very complex. And the main point is that what's happening is that usually in thermodynamics, one goes from sort of this low entropy state to this apparently higher entropy state. And what's really happening is that the evolution of the system is sort of encrypting the initial conditions to the point that you can no longer tell that by any sort of practical process of observation that there was a simple initial condition, a low entropy state from which the thing came. Let's talk about another sort of implication of the principle of computational equivalence, and it has to do with intelligence. So another issue is if we look at science, we have different kinds of models for different kinds of systems in nature and so on. Ultimately, when we look at physics, for example, we'd like to sort of drill down and say, well, is there a fundamental model at the bottom of physics? Well, you know, Descartes was pretty sure that within 100 years there'd be a fundamental theory of physics found. Turned out that wasn't the case, and something bad seemed to happen. It seemed like every time we get to another level of fundamentalness in physics, the models that we have to use get more complicated. It seems like, and that kind of gives us the sense that maybe there's no bottom to this process of going to more fundamental levels in physics, that maybe there isn't an underlying simple rule for the universe. Well, there's a question of, you know, should there be a simple rule for the universe? I think one of the things we know about the universe, something observed from, you know, a long time ago by theologians and so on, and you know, sort of the argument by design kind of approach and so on. One of the things that's a fundamental fact that we know about nature is that there is order in the universe. It might not be that way. You know, there are maybe 10 to the 100 particles in the universe, and it could be that every one of those particles gets to do its own thing. That there's no overarching set of rules, there are no laws for the universe, it's all just random. But in fact, we know that the universe is, at least at some level, quite orderly. So the question is, how orderly is it? Is it so orderly that there's a tiny rule that could be represented by, you know, 3 lines of Mathematica code, or is it just somewhat orderly, where there's a quintillion line program that represents what the universe does? So we don't right now know the answer to that. We don't know sort of how big the program for the universe might be. But already just thinking about a very small potential program for the universe, there are many implications of even just the very idea that there might be a small program for the universe. For example, as soon as the program is small, sort of all the different, it's impossible to fit all the specific things that we see in our universe and that we're used to into that program. If the program is 3 lines long, we don't get to set in there, you know, the mass of the electron, the number of dimensions of space, the details of such and such an equation and so on. They all have to be crushed down to something where they're all connected. We don't get to sort of adjust our universe arbitrarily. And that also means that the distance between one small model and the next is very large. So the chances are that one model is going to give a universe that is, once we get a universe that's roughly right, and if the model for the universe is simple, it's likely to be exactly right. Because the distance to the next nearest model is huge, And it'll be the difference between having a universe with 3 dimensions of space and a universe with, 11.2 dimensions of space or something. And many other much more radical changes. So I've been interested in the question of, out in the computational universe of possible programs, does our physical universe exist out there? And if so, how far out is it in the computational universe of possible programs? Well, it's one of the things that I sort of wonder about. It's not clear, how Copernican the situation is. It could be the case that, one of the things that's happened over the course of science is the realization that things that we thought were special about us are actually not that special. We thought we were, life, we were, at the center of the universe, things like that. Turns out that's not true. We thought that there was something incredibly special about, the chemistry of life. Turns out that's not really true either, and so on. So, you might think based on that, well, it's got to be, the situation with universes has to be sort of Copernican too, that it couldn't be the case that our universe is special in the space of all possible universes, that out in the computational universe of possible universes, that our universe should somehow be a special one. I think that, I don't know the answer to that, but it seems like it's worth at least looking in the space of all possible universes to see whether our universe is one that is tolerably simple and that could perhaps just be found by searching the space of possible universes. Well, when you're in the universe hunting business, you have to have kind of some sort of basis for the underlying models that you use just to sort of prune the search. And one of the things that, as I mentioned, as soon as you are sort of trying to crush all the physics into a tiny program, the things that are familiar in physics as we usually practice it won't be visible. I think the most reasonable kind of way to start, and there are a variety of different possibilities which I think are ultimately equivalent, is to think about sort of the universe as being like a giant network. It's kind of funny, actually. I realized that, so space becomes sort of deconstructed into this network of possible points, that they don't live in any particular dimension of space. It's just that on a very large scale, this network will behave, in effect, like a space that might be 3-dimensional or whatever else. It's a little bit like a fluid, like water. Ultimately, there are a bunch of discrete molecules bouncing around, but on a large scale, the thing appears to be sort of a continuous phenomenon. And so, for example, as you arrange the network in different ways, it might behave as if it's 1-dimensional, 2-dimensional, 3-dimensional, whatever. It just has some structure. I actually realized that this kind of view of space, if we look at sort of the progress of mathematics and science and so on, a big step happened when people realized that Euclid's axioms, that the 5th postulate of Euclid about parallel lines wasn't a necessary thing for sort of the consistency of geometry and so on. And that was when one was able to start thinking about curved space and so on. What I realized is that the very first common notion of Euclid, which is a point is that which has no parts, a point is something indivisible with no pieces, it's that first common notion of Euclid that we are now thinking may not really be necessary, may not be really how the universe works. In a sense, we're sort of deconstructing the notion of even points to think about what space is like. Imagine this is what space is like, some very giant network like this. Matter, particles, things like that become kind of features of this network, little sort of twists in the network and so on. We think about what time is. Again, time is something that sort of the models that we have are beneath both space and time. And so one view of time is to think about sort of this network kind of updating itself. It has some rule that says whenever there's a piece of network that looks like this, it should be updated to be a piece of network that looks like that. And let's just say we ignore the notion of sort of a clock that's ticking forward and making time progress. And we just say the network's just going to update itself wherever it feels like according to rules like this. Well, it turns out for certain kinds of rules that there's a phenomenon I call causal invariance, which implies that even though the microscopic rules by which the network updates can sort of happen in different places, the causal network of how one event affects another turns out to be invariant with respect to these underlying reorderings of what's going on. And if you're into mathematical logic, it's kind of related to the Church-Russell property and things like that for systems. So what happens, so in fact, whenever there's causal invariance, it turns out there's a big prediction you get to make about these systems. When there is causal invariance, it implies that in a certain limit, special relativity is valid. Non-trivial prediction. It's nobody's ever had a physical model that has this feature that you can derive special relativity from something more fundamental. But this is a case in which you can do that. Actually, you can even go on and you can even show that in the same sense that in sort of the same general way that one derives the fluid equations from the microscopic dynamics of particles bouncing around in a fluid, one can also derive, it turns out, equations of gravitation, Einstein's equations, in a certain limit for a large class of systems of this type. So that's kind of exciting. It kind of suggests that it's not completely crazy that one can set up a system like this. But so what does it look like on kind of the front lines of the universe hunting business? What one's doing is one's enumerating possible universes, possible sets of underlying rules, and then the question is, given a particular set of underlying rules, does that set of underlying rules correspond to our universe or not? Well, as you just enumerate these things, most of them are definitely not our universe. You can say in an instant, this isn't our universe. The thing has no notion of time, it has no notion of space, space expands exponentially, nothing has an effect on each other, and all these kinds of things. It's obviously not our universe. But it turns out you don't actually have to go very far, a few hundred universes maybe 1,000 universes, before you start finding things where you grow them for 1 billion steps in your computer, it's bubbling around, it's got, 500 billion nodes flapping around. It's very complicated. You can't tell what's going on. And in fact, computational irreducibility really bites you here, because in a sense, to know whether this corresponds to our universe, you might in effect have to run it for as many steps as our universe is run for. And that's not a practical thing for us to do within our universe, for example. So what you have to do is sort of recapitulate the history of physics in an automatic way, looking at this kind of candidate universe and trying to figure out its effective physical laws and see whether they correspond to the physical laws of our universe. So in any case, that's a process that one can go through. It's sort of interesting. I can say that within the first 1,000 or so universes, there are candidate universes in the computational universe. There are already cases where I can't say for sure that this isn't our universe. And it's an interesting topic, how one sort of progresses with that and how one has to hope for certain pockets of reducibility that occur there. So this sort of question of where is our universe in the space of all possible universes, interesting question. We don't know the answer yet. Perhaps we'll know. Perhaps at some point we'll know that it's number such and such in the space of all possible universes. My guess is that the question of where our universe is in the space of all possible universes will end up having a more complicated answer that has to do with something like it's actually across a very large collection of possible candidate universes. There is a certain kind of equivalence that means that our universe is any of a certain set of universes, and it'll be because the observer is within our universe that we sort of can't tell that it's all still equivalent, even though the actual underlying laws are different. But this whole question about where do things occur in the space of all possible whatevers, there's another case I just want to mention because I think you might find it interesting. In mathematics, the whole field of mathematics, we can ask, we think of mathematics as this sort of foundational area that kind of covers formal systems of all kinds. But there's sort of a question of, is that really right? And, one of the features of mathematics is that it's also a system where there's sort of a fairly small set of underlying rules, a fairly small set of axioms. On this page are basically all the axioms that are used in standard mathematics today. And from these axioms have been proved about 3 million theorems in the literature of mathematics. And there's a question of kind of, can we actually generalize mathematics? These are particular sets of axioms that have been used in mathematics. What about the space of all possible axioms for mathematics? Well, we can just go ahead and start enumerating possible axiom systems in mathematics. This is sort of an ultimately desiccated, deconstructed version of mathematics. Down the left are possible axiom systems for mathematics. Across the top are theorems that might be true. And so effectively every row of this picture is a possible field of mathematics. And there's a black dot whenever a particular theorem is true in that particular field of mathematics. And so one of the questions is, this is sort of the space of all possible mathematics is. Let's take the mathematics that we actually use. What's special about that mathematics? Well, I think, so one way to sort of test that, one way to ask that question is, where does our mathematics lie in the space of all possible mathematics is? And so, for example, let's take an area like Boolean algebra. We can ask, where is Boolean algebra? What axiom number is Boolean algebra? And the answer is, traditional axioms for Boolean algebra, it's way out there in the space of all possible. If we start just enumerating axiom systems, the traditional and or not axioms for Boolean algebra really complicated. But actually, it turns out you don't need axioms as complicated as that for Boolean algebra. And actually, a number of years ago, I did a big search in the space of all possible axiom systems, and I found that about the 50,000th axiom system that you reach, just that single axiom at the bottom there with 6 nands in it, turns out to be the minimal axiom, and from that axiom you can derive all of Boolean algebra. So this tells us that in the space of all possible axiom systems, Boolean algebra, this logic, propositional logic, lies at about the 50,000th place in the space of all possible axioms. So that sort of gives us a sense of where our mathematics lies in the space of all possible mathematics is. You can ask, why did our mathematics, what is special about our mathematics? I think ultimately what's special about it is kind of the history that in ancient Babylon, people started off with arithmetic and geometry, and they had particular ways to generalize those ideas, and the generalizations of arithmetic and geometry are modern mathematics. And they're kind of a tiny island in the space of all possible mathematics is. Oh, you might say, well, the mathematics that we use is mathematics that's relevant to the natural world. That's not a good argument, because we actually now know that there's lots of different systems in this computational universe, effectively in the space of possible axioms and so on, that are highly relevant to the natural world, to modeling the natural world, that don't happen to be the ones that exist in traditional mathematics. So anyway, this is one of these cases where we can kind of look at what's interesting out there, and we can ask the same question in biology. What does biology choose? Actually, biology does a much better job at sampling the space of all possible programs than something like mathematics does. Well, so let me return to questions of intelligence and so on. So one of the things that that you might ask, that the principle of computational equivalence starts talking about, is to ask something about what do we mean by having a system that's intelligent? Well, I always think it's a very slippery kind of thing. I mean, it's like when we define life. There's a very easy historical definition of life, because every example of life on Earth has the same sort of genealogical history, and it has the same details about RNA and cell membranes and who knows what else. But if we say abstractly, we've sent a space probe to Mars. When I was a kid, there used to be, that was the first time that was done, and it was sort of digging up little pieces of soil, and the question was there an abstract test for the presence of life that was abstracted from the details of RNA and all these kinds of things? Well, in ancient Greek times, people would say, if a thing could move itself, it must be alive. That clearly not, you've got steam engines, clearly not correct. Later on, it was a thing that can reproduce itself, must be alive. Well, then we have all sorts of things, including, computer worms and all sorts of things like that. It's pretty clear that self-reproduction is not the defining characteristic of life. So ultimately, what we realize is that the defining characteristic for us of life is this very historical definition that involves the particular details of the evolution of life on Earth. And so it is, I think, with intelligence. I think that when we try and sort of abstractly define the notion of intelligence, we realize that the one thing that definitely is there's got to be computational sophistication. Without that, you're clearly not looking at an example of intelligence. But beyond that, there's the question of, is there something special about, is there something that you need beyond that to make intelligence? Clearly, human-like intelligence has a huge historical set of historical details, all interwoven with biology, with our civilization, with all sorts of things like that. And you might say, well, what's important, for instance, is a notion of purpose. Well, we can talk about that. That's a whole nother elaborate set of issues about what do we mean by purpose. And ultimately, there's this sort of thread of purpose that I think gets defined by the history of human civilization and so on. So, as a practical matter, you say, well, let's think about this sort of test for intelligence. Let's imagine that we detect extraterrestrial intelligence. How do we know whether what we're seeing is something intelligent? We might say, if we detect the Fibonacci numbers, the primes, the digits of pi, something like that, my gosh, that must be an example of something that, what could be the cause of that? Well, with our sort of traditional intuition about things, we might say, well, to get something as sophisticated as that, the only possible explanation is that there's this giant history of the development of a civilization with all kinds of technology and mathematics and who knows what, that gets to the point where we can produce that sort of complexity of output. And indeed, if you look historically at examples, an example I kind of like, Marconi, one of the inventors of radio, had this yacht that he used to go up back and forth across the Atlantic in, and when he was in the middle of the Atlantic, in his radio mast, he heard all these weird kinds of complicated sounds, complicated radio signals. And actually, his first thought, and I think Tesla thought this more seriously, was that these must be signals from the Martians. Okay, so he assumed that that was an example of intelligence, that to make something that complex, it must be an example of intelligence. But in fact, it turns out it's just physics. It's just the processes that go on the ionosphere produce this kind of complicated output, and that's what you're seeing. So the issue is there a sharp distinction to be made between sort of intelligent sources and sources that just show computational sophistication? It's similar when we say, the weather has a mind of its own. That's kind of us attributing to the weather, to the sort of complexity of the weather, something that is mind-like. And what one realizes from this principle of computational equivalence is that actually that sort of thing isn't as crazy as it sounds. There is, in some sense, some sort of computational sophistication to these systems that makes them, in some real sense, kind of mind-like. So, well, and when it's also interesting from sort of a point of view of history of philosophy and so on, that when we think about the whole universe, and we think about sort of models for the universe, and we think about sort of the computational sophistication of those models compared to the computational sophistication of brains, there's again this kind of equivalence between the universe and its kind of intelligence, in a sense, and the intelligence that we see in our brains and so on. Well, anyway, so there's this kind of thing that you get from this principle of computational equivalence, from this kind of empirical study of the computational universe. You realize some of these things about sort of that are kind of sort of philosophical conclusions about things. Well, one of the things that I realized, so to speak, is that my first idea for trying to build something like Wolfram Alpha was you have to make a whole AI. You have to make something that has sort of human-like intelligence and so on. But then I realized there isn't anything like that. It's not something, we can build something. We will be able to build something, and it will evolve from many of the technologies we have today, that sort of any of the features of human-like intelligence that you want to put in, we'll be able to get. But it's something where, and it won't even seem terribly surprising to people. It will happen fairly gradually, and it will be something that, but it will be in a sense, what I realized was that what you need to do to sort of make knowledge computable and so on is something that it requires intelligence-like stuff. But that stuff is, in a sense, just computation, because there really isn't anything more that you could have in there. It requires sort of adapting to human-like attributes, for example, adapting to human natural language and things like this. But ultimately, what's inside is just computation. It's not something special to intelligence. And so that sort of philosophical realization, which I have to say is a post facto the realization of what was going on, as is often the case when one thinks about things. But I realized that that's sort of the philosophical underpinning that makes possible the idea that building a Wolfram Alpha isn't completely crazy, because if one had to build the whole AI, one knows that one's a long way from sort of doing that. But in fact, it turns out there's a more direct route that just uses kind of the pure idea of computation, so to speak. Well, I notice that I'm running out of time here, so I should probably wrap up and be happy to have a discussion, try and answer questions and so on about the world of the computational universe or other kinds of things. So thank you very much.
Okay, I think it's time to take a few questions. You might try to face the camera there when you ask your question, although it's not certainly necessary. And I'll come with the microphone. So who's going to be first? Okay, can you just introduce yourself and ask the question?
Thank you for this talk, Michał Paradowski, University of Warsaw. I'm a linguist. I have three very brief questions. One, well, the cellular automata process in a serial manner. That is, you could see them operating step by step, whereas much of what humans do is parallel and involving multimodal processing. So how would you reconcile these two things? The second thing, most of the things in nature are pretty robust to perturbations and can mutate, adapt. When you've got a cellular automaton and you change the color of one cell in it, you end up with a totally different pattern. So you could say that it breaks down. And the last thing is, how is Wolfram Alpha different from Watson in terms of the ontology and in terms of the query processing? So could it beat Watson in Jeopardy? Thank you.
Okay, let's see if I can remember all these questions. So first, the first, by the way, there's some strange.
The first question was about parallelism.
No. I've got the questions. I was distracted by something displayed on the screen about the remote camera. So the first question is about parallelism. So actually, people usually say cellular automata are a great example of parallel computation because all the cells are updating things in parallel, as opposed to something like a Turing machine where things are happening one active cell at a time. But if you say, well, cellular automata are special because they have sort of local connectivity in the computation, yes, absolutely, they are special in that way. What's interesting about the sort of phenomena in the computational universe is that they are completely unaffected by all sorts of changes that you might make in the underlying model. I mean, I don't know, here's an example, for instance, of a register machine, which has no locality of any kind. It's just sort of an arithmetic game of a sort. You can make cellular automaton-like things that operate on networks. For example, those models that I was showing you of fundamental physics are based on having a network where things are connected sort of in an arbitrary way and being updated. And again, the basic phenomena don't change. Now, in terms of, you talk about kind of multimodality in human processing. I'm not quite sure. I mean, I know what that means in the sort of technical sense, but I'm not quite sure how to relate what we might build in technology and in computer programs that sort of do multimodal kinds of things with what sort of the underlying sort of basic science models are. But I don't think that there's anything we can start thinking about. What we realize is that we look at something like this and we can say, well, there's all sorts of things going on here. At one level there's a background that behaves in such and such a way, and it's characteristic of one kind of processing. At another level there are these little things that are interacting in such and such a kind of way. They're characteristic of another kind of processing. What we realize is that there's sort of that within these systems there emerge these different kinds of processing and so on that we can identify. When we try to understand these things as humans, we can break them down into several different kinds of processing and so on. So you asked about kind of the effect of perturbations and noise and so on. I think one of the things you have to realize is that lots of models that have been made for natural systems are stochastic models, probabilistic models, models that involve some sort of random element. In a sense, whenever you have a random element in a model, it's sort of a wimp out. Because what you're saying is, we just don't know how such and such a piece of our model works. So let's just assume that there's something from outside our system that is kicking our system in some way to perturb it. That's kind of the nature of a probabilistic model. One of the things that's interesting is to hold oneself to sort of a higher bar in terms of making models and say, let's just model the whole system. Don't allow anything to be sort of kicking it from the outside. And for example, one thing you realize is that when you actually run simulations of systems, you're probably these days a lot of the time using precisely Rule 30 to actually generate these supposedly random numbers in these simulations. And you could say, well, why don't we just combine that? Why don't we just realize that within the system itself there is actually a process of randomness generation that is, again, deterministic? Well, you can ask at a practical level, kind of if you take something like a cellular automaton and you say, let's perturb it, let's kick it a bit, let's say, how robust are the phenomena that we see here? Well, there's a whole rich phenomenology of that. There are all kinds of phase transitions that happen. You can apply a certain level of noise and some things will be preserved, and then above that level of noise, things will all disintegrate and so on. It works pretty much the same as it does in lots of other areas of statistical mechanics. I think what one has to realize is that many of the features of the system are unchanged by those underlying small perturbations. So for example, I've studied a lot fluid mechanics, where the question comes up very strongly, when you see turbulence in fluid mechanics, what's the sort of fundamental origin of that apparent randomness? Is the fundamental origin of that randomness something that is in effect from outside the system? So for example, it could be that the randomness comes from molecular chaos, from some kind of thermal fluctuation in the molecules that somehow amplified up to make this randomness on a large scale. Or it could be that chaos theory is right and that there's some small perturbation in the initial conditions that we're sort of steadily excavating to see the randomness in the outcome of the system. I think in most of these cases that's not what's going on. In most of these cases what's going on is actually a completely repeatable randomness, as repeatable as the digits of pi if you did the experiments carefully enough. But nevertheless, there's an intrinsic process, like in Rule 30, that generates randomness. So it's sort of distracting to have a model in which you're kind of putting randomness in from the outside, because that's really not most of what's going on. And you get to see there's a very definite scientific test for whether there's randomness coming from the outside or not, which is is the system repeatable? Because something like Rule 30, it's precisely repeatable. Every time you run Rule 30, you're going to get the same pattern. Unlike something where there's, quotes, noise from the outside, which wouldn't be repeatable. So the third thing you asked was about relationship of Wolfram Alpha and the IBM Watson project. Let me show you something there. The IBM project, and I know the people involved in it and have been following sort of the history of such things for a long time, is kind of an evolution of a kind of direction of the kind of information retrieval, text retrieval tradition of computer science. And actually it's the same lineage that led to search engines, but they kind of broke off maybe 20 years ago and went in slightly different directions. So kind of the idea of Watson is you've got a big corpus of texts and you chop it up into little snippets, and then the real challenge is, given a question that comes in, can you match something in the question that comes in with a snippet from the text corpus that you had ground up? So that's kind of the idea, and the main innovations in Watson had to do with scoring how good the matches were between the text snippets and the corpus and so on. Well, that's a fine sort of statistical way to approach things, and kind of if you watch the Jeopardy program, you could see actually in some of the candidate answers, you could actually see kind of funny capitalization and so on that came from the raw text snippets that were used, that were ground up to make candidate answers. So that's kind of the approach there. It's take the corpus of knowledge, grind it up at a textual level, and try and match things up. What we're trying to do with Wolfram Alpha is, in a sense, much crazier, much more ambitious. It's to take the input question and to actually turn it into some computable symbolic representation, to then have actual structured knowledge that is represented in a completely computational way, and to compute the answers to these questions. We're not trying to match anything. We're trying to compute the answer to the question based on sort of actual kind of computationally represented knowledge, and to do that by actually understanding the raw linguistic input. So for example, in Wolfram Alpha, any piece of linguistic input that you put in turns into internally some symbolic expression represented in the mathematical language, which can then be computed from to try and generate an answer. So that's kind of the approach that we're taking. In terms of how well could we do on Jeopardy, right now we did better than I would have expected, but it's completely a different kind of thing. It's actually interesting, if you just look at standard search engines, you feed Jeopardy clues into a standard search engine does surprisingly well in doing this matching task of connecting kind of a snippet with something that exists out there on the web. But that's a very different kind of objective from the objective that we have in Wolfram Alpha of being able to compute the answers to questions sort of, I mean, one very big distinction that should be made is that a search engine, the web, IBM Watson, all of these kinds of technologies, they're all about taking sort of existing answers that have been written down somewhere on the web and being able to successfully regurgitate them on demand. What we're interested in Wolfram Alpha is something different. It's about actually computing from scratch things, whether or not anybody has ever written down that answer before in sort of the history of the world. It's about just being able to take knowledge and compute from that knowledge sort of fresh new answers to questions.
Okay, I think that was a pretty comprehensive answer. I'll take the advantage of holding the microphone to ask the next question. So this is Dimitri Kazakov, University of York. And my question is this. people have been trying on and on to come up with a universal modeling paradigm that is universal as possible, so covering as well, in a sense, related to philosophy in the sense that it can relate to anything we can discuss, but on the other hand, somewhat more productive so that we can actually answer questions with some level of certainty and specific questions at that. And for instance, when discussing, say, systems theory or differential equations, related, and when people looked into the nature of, say, life or complex systems that become increasingly more complex, the point that, say, Ilya Prigozhin made was that we need a certain class of these systems, the open dissipative systems, to produce this kind of systems where we have an increasing level of complexity that we probably would also expect from an intelligent agent, intelligent system. So my question is, in your digital cellular automaton world, what are the conditions, what is the subset of systems that corresponds to this open dissipative set of systems, or what is the source of negative entropy, if you want, that would make them so?
Well, so I think the first thing to say, so when I first was interested in how complexity arose in nature, the first two problems that I really worked on were, how does the universe go from kind of the hot Big Bang to this thing with lots of galaxies and other kinds of clumpy structure and so on in it? That was one thing, and the other thing was about brains and how they worked. And I was very interested in Prigozhin's work and got to know him a little bit, and tried to sort of, and thought that the right way to approach these kinds of questions was as sort of a generalization of the second law of thermodynamics, as something which used sort of statistical mechanical methodology. And I realized at some point that that wasn't right. In fact, in a sense, I mean, statistical mechanics is a very mathematics-based, very specific set of methodologies around sort of the phenomena that we're talking about here. When you talk about negative entropy and so on, I mean, there's a lot of different concepts that are bundled together in that, and it's sort of a complicated story how to unravel it all. I think it's fair to say that when we look at a system, when I was first interested in these things, one of the things I was most interested in is how one went from a random initial condition, for example, in this case here, from the randomness of the initial condition, the sort of maximum entropy random initial condition, to the non-trivial structure that you see evolving here. Well, you might have had to go through some whole mathematics-based thing about open dissipative systems and so on. You don't need any of that. This is a great example of where you go from complete randomness in the initial condition to all kinds of non-trivial structure. You can get sort of, you can see the evolution of sort of arbitrarily complex stuff in a system like this. You don't even have to go very far in the computational universe before you find things like this. And that's sort of one of the things you realize from the methodology of just going out into the computational universe and looking at things, that you discover all the stuff that you didn't know was there. You might have imagined that you have to engineer a system that makes complexity by doing some kind of thing with dissipation and, you know, who knows what. But actually it isn't true. They're just these systems lying around all over the place. And this is an example of one of them. Now, you can then go and, so I think that's the main answer, that there's sort of a more general phenomenon that you can readily see that doesn't require all of that structure, I think.
Thank you. Next question. Yeah, and then Mark Bishop.
Hi, thanks very much. Michael Beaton, Imperial College and University of Sussex. I'm not an expert in what I'm going to ask you about, but you talked about using the space of possible programs as a way of finding the most general system for modeling reality. Doesn't David Deutsch, as I understand him, argue that the behavior of quantum systems can't be correctly modeled anywhere in the space of all possible programs? And related to that, you said something like, what's inside intelligent things is just computation, it can't be anything else. But that sounds a bit equivalent to suggesting that it's sufficient to model intelligence to just use something with local hidden variables, whereas real physical systems can't be modeled with local hidden variables.
Okay, so about quantum mechanics. So one question that you might ask is, you're shown a system, and by the way, I've discussed this at great length with David Deutsch, so but I don't claim to understand all of his positions on these things. So, okay. So the systems that I study are in many respects, for fundamental physics, are in many respects completely deterministic systems. They're systems that, according to sort of the philosophy of quantum mechanics, they've got to be complete nonsense. It's got to be the case that no deterministic system could ever model quantum mechanics because there are these features of determinism that seem to imply experimentally observable effects that are not observed and that are violated by what we actually see in nature. Well, okay, two things to say as a preamble. First is that the systems I'm studying actually have some slightly not quite deterministic things that go on because of the way that they can have these sort of arbitrary updating orders and so on. But that's a detailed footnote. You don't even need that footnote for what I'm going to say next. So it turns out that the sort of the big thing that is supposed to be kind of the kind of the shadow of determinism in large-scale observable phenomena is the violation of Bell's inequality in quantum mechanics. And turns out that if you look at kind of the proof of the violation of Bell's of the fact that deterministic systems can't violate Bell's inequality, there's a very important footnote in that proof. And the footnote is basically space has to be a finite dimensional thing, like a three-dimensional space or something. Well, it turns out in these systems that I'm looking at, it isn't true. When you get rid of Euclid's first common notion about how space works, you no longer have this issue. And so, for example, what happens in the systems that I'm looking at is that, in effect, space is approximately three-dimensional, but there are these little threads of connection between different parts of space, which you might think of as sort of non-locality. That's not really the way to think of them, because it's just the way that space works. And those allow one to sort of connect things that would otherwise not be connected. Now, it turns out, even more interestingly than that, and I'm not sure if I can immediately pull up an example of that, when you start looking at how particles work in these underlying networks, you start seeing precisely phenomena that are like quantum mechanics. So what ends up happening, a sort of typical example, slightly technical, is to say, imagine a case where the network is planar, where you can lay it out so that no two wires have to cross over. So it turns out there are certain update rules that preserve planarity. And it turns out that whenever you have non-planarity, it's a theorem of graph theory, that every non-planar graph must have in it a K33 subgraph. So you can move around where you say that K33 subgraph is, but every graph that's non-planar must have one of these things in it. And that's very much like what happens with particles in quantum mechanics, that you don't get to say the particle is right there, it's just somewhere in here is a particle. When you start looking at interactions between these non-planar lumps in a planar network and so on, you start seeing some things that have a lovely analogy, at least with quantum mechanics. Can we reproduce all of quantum mechanics? Not yet. I think what we realize is that quantum mechanics is this sort of bundle of mathematical ideas that has kind of where a lot of things come together. A lot of things about mechanics, a lot of things about specific sets of variables and so on come together. And so what ends up happening is that the thing that okay, so in physics, at an underlying level, materials tend to get made of atoms and molecules and things like that. A bunch of physics that got developed a long time ago is rigid body mechanics, where we have a small number of degrees of freedom of rigid bodies, and we get to do fairly simple mechanics of those things. The analogy of quantum mechanics is to rigid body mechanics. The more sophisticated version of quantum theory is quantum field theory, which is the analog of fluid mechanics when you look at molecules. And fluid mechanics, getting from the underlying molecules to fluid mechanics is much easier than getting from the underlying molecules to rigid body mechanics. And so it is with quantum mechanics. You end up being able to get to quantum field theory more easily from sort of the underlying stuff underneath than to quantum mechanics. And in fact, these issues, like the violation of Bell's inequality, are not understood at all in quantum field theory. They are the creatures of the complicated limit that's taken to get to quantum mechanics. So, this is a complicated area, but I have to say that the first thing is that, from a formal level, the violation of Bell's inequality simply it's not an issue for systems that are not based on fixed dimensional space. And the second thing is that certainly at least at an anecdotal level at this point, we can say that the sort of the signatures of quantum mechanics seem to be starting to show up in these systems, which I think is very interesting and encouraging. Now, you also asked about intelligence, and is intelligence just computation? Well, intelligence as we experience it is this whole giant chain of history. I mean, if we look at Wolfram Alpha, for example, it does sort of perhaps some slightly intelligent-like things, and my gosh, it's not in a sense just computation. It's it's 20 million lines of code created by humans. It's gazillions of terabytes of data and things flowing in and so on, based on the world as it is, and all these kinds of things. Lots of essentially sensory data coming in from the world that sort of contribute to what it is. So in a sense, it's not just computation. The raw material from which it's made is computation. To get to something that is sort of human-like intelligence requires this kind of big pile of sort of essentially historically determined knowledge and so on. Now, the question of whether there's sort of quantum mechanics somehow involved in intelligence and the brain and so on, I doubt that there are. I mean, I doubt that there's anything terribly fundamental about brains that uses quantum mechanics beyond the way that quantum mechanics is already used in sort of the fundamental dynamics of physical systems. I mean, conceivably, there are things, one of the things that one wonders about, that's sort of notable about quantum mechanics is that there's sort of a source of randomness in something like radioactive decay. Actually, that's a big mess, because when you think it's random, you have to worry about sort of what correlations get induced by the measuring device and so on. I don't think that brains probably have in them sort of randomness generators that are based directly on sort of quantum phenomena and so on. One doesn't know yet for sure, but I'll be surprised if there's much that's fundamentally quantum mechanical, and certainly that uses any sort of philosophical implications of a lack of determinism in brains and so on. I think that such questions, right now, it seems like you could still say, well, there's something very, very special about the brain. Just like in the past, we've said there's something very special about all sorts of things to do with the human condition relative to nature. I think as technology progresses, probably even in the next decade or so, already, if you went back and you brought somebody from 50 years ago, if you brought Alan Turing back today and you said, okay, has artificial intelligence been achieved? Looking at many of the technological systems that we have, one would say it's a spectacular success of artificial intelligence. But there are still plenty of things where that hasn't happened. I think what will happen over the next decade, and this is a whole different discussion about technology futures, I think that the symbiosis of humans with machines will accelerate considerably. I mean, right now we already outsource a lot of our tasks to machines. We're starting to outsource a lot of memory to machines effectively. We're starting to outsource a lot of kind of processing that we do to machines. That symbiosis will accelerate, and in fact, there'll come a point where the main thing the human adds is figuring out what the point is. What are we actually trying to do? A lot of what we actually do will be done by computers, but we get to take that sort of thread of purpose that's been kind of the thing that's been developing throughout our civilization, and apply that thread of purpose to determine which of the infinite set of possible computations we might do we will actually choose to do. I have to go fairly soon, so I'd be happy to answer a couple more questions. Yeah.
Hi, Mark Bishop from Goldsmiths College, London, UK. I think there's kind of an elephant in the room, which I know you've thought lots about. So I've really got two really naive, simple questions that I'd be very interested to hear you clarify. And that elephant in the room is perhaps the notion of non-Turing computability. And it perhaps leads to just two simple questions of these. If the set of computable functions is countable, the set of non-computable functions is infinite.
Wait a minute, you just trailed off. I stopped being able to hear you. I got the set of computable functions is countable, and then silence.
Infinite. And if the set of non-computable functions is uncountably infinite, why then should all interesting questions of intelligence, the world, and indeed the universe itself be computable? And secondly, have you any remarks to say about ideas about the putative non-computability of the mind from, say, philosophers such as John Lucas, or physicists and mathematicians like Penrose?
Like who was the last person mentioned?
Penrose and Lucas.
Yeah, okay. So, non-computability, sort of going beyond Turing and so on. It's funny. I don't think that in 1936 the universal Turing machine seemed like much of a big deal, because people had kind of assumed, there were these different models of computation. First there were primitive recursive functions. It seemed like they might cover all the functions. Then, then there were general recursive functions. Then there were Turing machines and so on. I don't think it seemed like, and Gödel, for example, thought that, he used general recursive functions, but that his sort of approach would really capture everything in nature. That wasn't clear at the time. Over the years, the surprising thing that was found was that all these different systems that people invented, whether they're Turing machines, cellular automata, register machines, symbolic systems of various kinds, they all ended up being equivalent to Turing machines. And so then one started to wonder, well, is this really all that there is? And could it be the case that, for example, physics is really more than that analog computers can really do more than digital computers and so on? Well, this is a question about the universe. It's not a question that can be answered by pure thought. It's not a philosophical question. It's an actual question about the universe. There's nothing theoretically impossible about a universe that has oracles in it and goes beyond what Turing machines can do and so on. But it seems to be the case, so far as we can tell, and maybe it's wrong. It seems to be the case. So far, there is no evidence that one needs to go beyond sort of the Turing machine idea to understand what's possible in our particular universe. Now, I've obviously looked at models that go beyond that, and it's actually sort of interesting because so the kinds of measurements that we're capable of making right now are very sort of Turing machine-like measurements. And when we ask ourselves, if we had a mechanism inside that was doing sort of beyond Turing stuff, could we somehow could we detect that in our outside measurements? And it's surprisingly difficult to do that, in my observation at least. But at least right now, all I can say is that the minimal hypothesis that has sort of developed over the last 50 years or so is perhaps Turing machines are all that's needed. Might be wrong, but that's, and what I can say also is that if you start enumerating things that sort of go beyond the Turing situation, I'm not seeing good observable consequences of those that sort of enmesh with the kinds of things that we think about in physics and so on. Now, in terms of Roger Penrose and John Lucas, let's see if I can, I'm really bad at representing other people's points of view here. I know Roger Penrose fairly well. I knew John Lucas a little bit when I was a kid, but since then I've only exchanged a few emails with him. I don't think I can really represent their views terribly well. I think that perhaps there's a certain desire perhaps to say that well, I remember. Okay, I'll tell you one. No, I shouldn't tell this story. I'll tell this story. It's fun. It's not really I remember years ago when this is a story that really has no intellectual content at all, but it's amusing anyway. Years ago when Mathematica was young, and I used to be even more of a micromanager of what we do than I am today. I was looking through the new registration cards for people getting copies of Mathematica and so on, and I it was always kind of fun because occasionally you'd find somebody that whose name you recognize from some place or another. It so happened that particular day there'd been an article in Time magazine about Roger Penrose and his then new book, in which the heading was something like, Roger Penrose says, computers are all dummies and can't compute anything useful or whatever else. Anyway, so I'm flipping through these registration cards, and what should I find but Roger Penrose's, I think, first Mathematica user registration card. And so I'm looking at these two things, the magazine article on one side that says computers are all dummies and aren't useful, and on the other side, Roger getting his copy of Mathematica, hopefully to compute useful things. So I thought that was a nice, that story has no intellectual content, but I'm just reminded of that story in connection with this. I think that it's hard to I think there's well, as I say, my point of view is that the hypothesis that we have that the Turing thing is all that's needed is a reasonable first hypothesis. Maybe it'll be proved wrong. Maybe it will turn out that one searches for a fundamental theory of the universe on that basis, and one just can't find it. Just isn't out there. But I think it would be embarrassing if we went through the 21st century sort of having the possibility of finding a fundamental theory for the universe that's sort of out there in this sort of Turing kind of space, and didn't look for it. If we do succeed in finding it, and we do succeed in determining that, as I say, one of the features of very simple models is if things are roughly right, they're probably exactly right. It's very unlikely that there will be a simple model that has the feature that the universe works almost exactly just like this, but has a miracle happening somewhere over on the side here. I think that, so, you know, if we find it, then we will have answered the question, and we will be able to say, okay, here's our universe, it's this Turing-like thing, and there's nothing more to discuss. For the time that we haven't found it, we will still have the possibility that the hypothesis that it's all just Turing machines is wrong.